We've seen that our rate law is very dependent on certain circumstances occurring in just the right way. Our reactions need a lot of variables to be just so in order to occur properly. In order to map that out, one of the things we can look at is the reaction energy profile. Every reaction is going to have a unique energy distribution over the course of its reaction. By understanding how that energy moves through that reaction, we can make a lot of predictions about it, and we can find a lot of ways to bypass things. The energy profile is going to be extremely important when we look at how a catalyst works, and it's going to be extremely important when we look at the thermodynamics of a reaction. In order to understand this energy profile, let's first look back at this reaction. We had our ball and stick model broken out in order to look at a methyl cation interacting with a hydroxide anion in order to form methanol. Now, when we looked at this, we realized that not only do these have to line up the right way, they also have to have enough energy to connect. But most reactions aren't just as convenient as a positive cation and a negative anion that want to be together. Most have bonds that are already created that need to be broken up. So this would look more like a chloromethane reacting with a hydroxide. This chloromethane already has a bond right here that needs to be broken before the hydroxide can come in and bond with the methane. So when we need to break bonds, what does that look like as far as the energy goes? Well, to look at an energy profile, we're just going to draw out a little graph here. We're just going to sketch this out. And we're going to label our axes. The first one is going to be this axis. We're going to say this is energy. So we're going to be tracking how energy is affected and what energy we need to have in order for a reaction to occur. Our x-axis is going to be what's called the reaction coordinate. The reaction coordinate is the certain spot within the reaction where things are occurring. So it could look like, while this reaction happens, this is our first part, so we could make a little mark on our graph here. Let's say this is our starting place. They're right here. And then this collides, and that would be this point right here, and breaks this bond. That would be this point right here. And then this bond starts to fit together. That's this point. It fits together all the way, and it's finished, and that's this point. And so what we're really saying with the reaction coordinate is we're saying there are different stages of this reaction. If we break down even smaller than just an individual step of a reaction, even within an elementary reaction, we can look at how the reaction is going, at what stages of the reaction are we in. It's like watching a car collision in slow motion and looking at how is the energy level adjusting at each part of this reaction. And so we looked at, just off the bat, our energy level is going to be at some flatlined area. You know, when we start with just our regular reactants, just off the bat, this is stable. It's not breaking apart, nothing special is happening, it's just sitting here normal. When the hydroxide approaches, this is still sitting here normal. So it's still normal. But once the hydroxide collides, our energy starts to go up. So our energy is going to go up. And when our hydroxide collides with enough force to break this bond, our energy is going to peak. And then, as the hydroxide forms a new bond, our energy is going to go to a lower stage. And so when we have an energy profile, what we're looking at is our initial conditions where things are stable. We have this flat line. And then when we break bonds, we have to put some amount of energy into the reaction. So this is really where we get our energy threshold from. If the energy of each reactant is only at this level, well, that's not going to be enough energy to break those bonds. And so even though this is a downhill slope right here, even though it would be more favorable as far as the energy goes for this reaction to happen, it can't happen because we don't have enough energy to break the bonds that are there. So what we need to have is enough energy to break past this hump. It's like we could go sledding, but first we need to get to the top of the hill so that we can slide down the hill. Even though this is technically an incline, we can't slide through the hill. There's a physical hill in the way of us sledding down to this lower incline. We have to climb the hill in order to go sledding down it. So in a reaction, the same thing has to happen. We need to have enough energy to get to the top of that hill, to get to the point where we can break those bonds in order for us to be able to naturally form our new bonds. So when we break bonds, we need to use energy. When we form bonds, we get energy back. So this is like any process. So if we break bonds, we use energy. So we'd have negative energy. When we make our new bonds, we're going to gain energy back. And so by looking at an energy profile, we're able to see a lot of information about the energy taking place in a reaction. Not only are we able to track how much energy we need to put into this thing, so maybe what temperature do we need to raise this reactant to in order to get a reaction to proceed, but we also are able to track how much energy we get out of this. So an application of an energy profile could be looking at different combustible fuels for an engine. I need to know what this difference is. So the difference in energy. I need to know this change in energy. If this isn't big enough, then it's really not going to be worth it to try and use this fuel. So there are a lot of applications of an energy profile. And we're going to be able to extrapolate this when we start looking at reactions in multiple steps.